Thank you. So I'm here to talk about Cowait and the lessons learned from trying to build a kind of job scheduler or batch job scheduler in Python. I'm Johan, and I work as a software engineer at Backtick Technologies. We are a software engineering consultancy firm with a focus on machine learning and data science. And besides that, we try to come up with some product ideas and develop on them in a spare time or in between projects and so on. And Cowait is one such project that actually started in 2019, I think, or 2020 maybe, in the pre-pandemic, early pandemic kind of. So, like I said, it's an open source tool, and it's supposed to help you build batch processing jobs and run them on clusters using Python. And we kind of envisioned it to be the easiest way to build, run, and maintain data-intensive projects in Python. The animations might be screwed on this. So anyway, we identified a couple of major problems that you typically run into when you're working in these data-intensive projects. And as you might know, like one of the like big things that we usually need to spend a lot of time on is to develop a good system for processing continuously incoming data nightly and so on. And for that, you usually need a lot of infrastructure and and a lot of the tools that you typically use, or at least at the time when we started this, were pretty cumbersome, and they have a lot of things that could be improved. And the first major one is that we wanted a more like iterative development process where you could build and run stuff locally on your own machine and get quick feedback. Because what often ends up happening is that you write some code and then you have to like make a commit, you have to push it to source control, and you have to wait for everything to rebuild, and then you manually trigger the runs. And over a long period of time, this will waste a lot of your potentially productive time. So it would be great if we could just like run it on our computers. Another big thing that we wanted is automated testing, what you end up building with the traditional tools is usually very tightly coupled to the scheduling program itself. So that makes it kind of difficult to run tests against your code. So we wanted some kind of decoupling where you can easily run and test the software alone. It would be nice if there was a good build process or something to help you build continuous integration pipelines and so on, to have to do less manual work to set this up. And so we wanted the tools to support it kind of by default. And another problem that you typically run into is dependency management. And I'm primarily talking about dependencies within the jobs that you're trying to make. And Python especially is kind of notorious for introducing dependency conflicts between different parts of your project. So you might be writing a bunch of tasks, and after a while you end up having two tasks that depend on different versions of the same dependency. And a lot of the times it just ends up being a mess. So while thinking a lot about these kind of problems, we realized that a lot of it could perhaps at least be solved by introducing a lot of isolation. And we wanted to isolate every job and build it into its own container, like a Docker container, basically. And have a structure where every task is a simple function, and each function runs in a separate container. And these containers should be completely decoupled from any kind of scheduler. So you should be able to like write something, build it, and then run it without running the entire scheduling stack on your own machine. And this will help you in many ways. Like if you have the standalone execution, you obviously get these faster execution or faster iteration cycles, because you can just write and run like you would do in any other project. They become easier to test if the tasks are just functions. Then it's kind of simpler to think about them. You can give them some input and make sure that the output is whatever you expect. And while building all of this, then we can kind of create tools to help you build these images, because otherwise it's going to be a huge pain. There needs to be something to aid in the creation of images. And that will also be a big benefit to this continuous integration pipelines and so on, because if you can use these build tools to build locally, then you can also use them to build in CI. And if you have containers, you kind of get isolated dependencies by default. You can run each task in a completely isolated environment. So just kind of to show what it typically looks like for the actual code that you're writing. It will look quite similar to many other like task scheduling systems. For example, here is 2 tasks defined in the same file, and it's basically one task that spawns 2 other smaller, simpler tasks. In this case, it's just a function that returns the square of a number, which you might not need to do in a distributed manner, but yeah. So you can spawn them, and then you can wait for them to finish, and you can work with the result. So like I said, it looks kind of similar to many typical solutions, but the difference here is that this can run completely independently of any scheduler or anything. You don't need any kind of setup. You can run it in Docker on your own machine, or you can run it directly on a Kubernetes cluster. So kind of just to illustrate a little bit, like what will actually happen when you run it is that the main function will run in one container, and it will create 2 completely isolated processes running perhaps on a different machine in the cluster. They will run, and then they will return the results back to the caller. And this also illustrates a little bit of what made this design interesting, because remember, the whole project kind of started as kind of a fun thing to try out. And so this entire design, that where the tasks are completely independent, is a little bit of a quirk and kind of something that is a little bit fun about this. And this is illustrating it. Like the main task starts other tasks, they connect back. And you could potentially have these tasks create even more tasks, and they will form like a big tree. And in the same way, you could write whatever code you want here. You could write a loop, and you can spawn as many as you want, and you can spawn them dependent on other variables. So you don't need to really like predefine what the entire like graph of tasks is going to look at beforehand. But yeah, like this kind of quirky design comes with a couple of disadvantages, which we kind of discovered along the way. And the whole thing was a little bit of an exploration to kind of find out if this is a good idea or not, because it has not really been done. And when something has not really been done, it's probably a stupid idea, but it might also be a brilliant idea. So like you never know, you have to work a little bit to find out. So like one kind of obvious disadvantage is that if you have a huge tree like this, and all of the information about what's going on has to flow back to the kind of top level tasks, then it kind of becomes more vulnerable to interruptions in between. Like if this one dies, then all of you're gonna lose contact with everything that's below it, so to say. And it also turns out that in many real-world projects, you actually need a scheduler to make anything useful. And we kind of left it for later. The vision was that the scheduler itself is also going to be a task. And everything can be a task. Like we can just make something that will coordinate the tasks, and it's all going to be work out in that way. But yeah, it turns out the scheduler is pretty important, and it's probably not a super good design to get rid of it completely. It would probably be enough to make it optional, so to say. And this was implemented in Python, which reintroduced some of the original problems that we were trying to solve, kind of ironically. One of them being that Python does not really have support for concurrency. You can't really do several things at once. And that can become a problem when you're, since the kind of background task management and the task itself is running in the same process. The task that you're running can kind of starve the background communication from resources, which can like make it lose connection and so on. You also have the problem that you might have dependency conflicts, which we were trying to solve. You might have dependency conflicts with the Cowait library itself. So yeah, it would probably have been better designed in a different language. And but it turns out that it's really fun to play with this kind of architecture where you can kind of just create tasks. And anything can be a task. You can run any container, actually, not only Python code. You can have it run like MySQL or Redis or Spark. We had it create entire compute clusters and so on the fly. And since it was just kind of fun to play with this, which gave the projects a little bit kind of a sprawling goals kind of problem. We had some scope creep in it because it's just kind of fun to try out whatever is going to work and what's not going to work. What's good about it is that it's actually really easy to run Python code on clusters, and a lot of the benefits that I talked about in the beginning are actually achieved in this. Like you get a really quick development cycle, and you can easily run it on the local machine, and it's easy to run it on a cluster. You can get started very easily. It basically requires no configuration, which was another primary goal. And you can use that to actually create some interesting distributed software. It has been used to create stuff that we did not really envision it being used for. For example, distributed web scraping, where you might want to load and collect a lot of data from the internet. You might want to have a lot of parallel workers downloading this data. And then it turned out to be a good tool for that. But then you have a little bit different requirements from the typical data batch processing, which we originally intended it to be designed for. That's kind of all I had in the slides. I don't know how much time we have. I might actually show some of the, I can demo it a little bit and also answer questions. Kind of leave it a little bit open as well. If you want to check it out, I think it would be a lot of fun if somebody wanted to try and play with it. If you want to run some code and try to make it do something interesting, you can check out Cowait.io. There is some documentation, not a ton, but there is some. And you can give us a star on GitHub. It's not really been advertised in any major ways. It's mostly like mouth to mouth, like this. So it's always fun. And do you have some questions, or should I show it in practice?
I do have questions, but I'm more interested in the demo.
Okay.
For the questions later.
Yeah. So maybe I'll just show like a quick. Like we have something that's very similar to the task that I showed in the slides. I think this one, it has a subtask that basically just return whatever you give to it, and then this is a task that will just return the smallest value. So it's still pretty stupid, like, but just kind of to illustrate how little code you need to make it do the basic basic things. This is a little bit different syntax. You can do the bare functions, or you can write it as the classes. And then to build it, there is the Cowait build, which will make this container image for you. So you don't really have to worry so much about all of the Docker stuff and so on. You can basically just tell it to build it. And then if you want to run it on your own machine, you give it just Cowait run. And yeah, it's still kind of difficult to see what's going on. So we did create a UI for it, which I'm not 100% sure if it works right now, because I have not tried it in a while.
Nice and colorful terminal you have there.
Thank you. So of course the UI, it has very limited features, but it does have dark mode and light mode. So let's see if it works, fingers crossed. Yeah, it does. So like this was kind of the idea for where to take this project to build more kind of scheduler features and so on top of it, where you can kind of browse through the individual tasks in this kind of tree. So this is the top level minimum task. And then it creates these two children, and this is like their inputs and whatever they returned and so on. So yeah, I don't know if I have any other more fun examples. Yeah, do you have any questions? Probably easier to answer questions than to really explain everything.
First question. How is it? How is data transferred from one task to another? Can you send classes? Can you send any kind of objects?
Did a little bit of work on that. You can send JSON primarily, and then we were starting to develop kind of a system to like marshal and unmarshal different types. So you should be able to send more complicated objects and have it automatically unpack them and so on. So you could send like data frames, for example, pass them between, or like a reference to a Spark cluster, for example. Because that was also one of the primary goals for this, was that it would offload most of the work to some kind of Spark cluster or Dask or something, and that the tasks themselves would basically only call out. So yeah, one of the primary goals was to like be able to pass this kind of stuff around. So what basically happens is that each task has a WebSocket server, and when it creates the subtasks, it kind of includes its own IP address, basically. And then the subtasks, when they spawn, they connect back up to the parents. And that's how it forms this tree.
All right.
Does that answer the question?
Yeah. And kind of my last question. How is the folder structure, and how does that, like, you have two functions in the same file? Does it package them together? Do they package in different files? How if they have different dependencies of like, how do you make sure that?
So there is actually a little bit of configuration. I lied earlier, but not a ton. There is like this YAML where you give it like the name of the image that it's going to build, and the root folder of the project basically becomes the context for Docker. So everything below this folder is packaged into the image. And then when you run, like when you do Cowait run, you give it the module name. So in this case, it's the file name, but it could also be like a Python import path. I think there are some built-ins like Cowait.tasks.shell, for example. You can run whatever you want. So that's one of the small quirks, that these top-level tasks, they can only have one definition per file, essentially. So it will run whatever task is in this module. And if you want to add requirements, then you can give it a requirements file. And the build system will pick it up. So it will find this custom requirements, and then it will build that into the image. And if you want, you can also like have it make your like a completely custom Docker file in the same way. So you can make Docker file, and you do yeah. So that's kind of how you can customize it a little bit, but it doesn't require a lot of setup to get going. And yeah.
All right. Thank you.
Hi, yeah, thank you for this. It was really interesting. You said that it's very easy to then take the code that you write with Cowait and execute it on a cluster. Did you mean Kubernetes? Or?
Yeah, so it deploys to Kubernetes.
How does it map to? Does it map every single task to a separate pod? Or
yes,
yeah,
basically. So it has two drivers, so to speak. It does have Docker and it has Kubernetes. And when you run the tasks on Kubernetes, they become pods. I don't know if I have a cluster that's I can actually use, but what you would basically do is you have to add a little bit of configuration for the cluster, and then when you do run, you just add like cluster hello, or whatever you call it.
Cool. Yeah, that's very nice. Does it persist tasks that I've run previously in the web UI? Is there any like persistent part that you would deploy somewhere, or is it just clients everywhere that spawn Cowait tasks?
So the UI thing was kind of meant to go there. It does not have any kind of persistence right now, but the UI is also a task. So you run it on the cluster, and then that was meant to preserve the history. But right now it just keeps it in memory. But it will notice that you're running tasks, and it will collect the logs and the history and so on.
Cool stuff. Thank you.
Thank you.
I mostly wondered if you had other examples of places where this architecture of spawning a bunch of tasks to do something and then quitting. I thought the web scrape was a perfect example.
Yeah, I think that's probably the best one. Like we used it to create Spark clusters as well, and but that was like something that was not really originally planned, because it's normally you don't want to do that, but it was kind of a fun thing that you could do. You could have the tasks basically create Spark workers and have them form a cluster that could then disappear automatically when everything is done. And yeah, you could have it run databases and so on. I think it could be useful for like setting up test environments and so on, and like tear it all down when it's done.
One test each.
Yeah. Might be slow, but
yeah.
I have one last question. Kind of the logical model of this whole code. It's more of a push based, where you kind of the root function has to know all the other functions for it to schedule the jobs correctly. So if we were to think of it as a kind of a DAG, then the starting point needs to know, like each step needs to know what the other step does, instead of I think the more commonly is to pull it instead. That the root doesn't need to know anything who is reliant on it, but instead the children knows their parents. Was that a conscious decision, or was it more just?
It was kind of a quirk of the design, so to say. We kind of thought of it in the beginning like, well, if you can write it as a DAG, you can probably write it as a function, which turned out to not really be very convenient. But it is basically push, in the sense that each task connects to its parent and it pushes the results. And in this sense, the tasks also tell their parents about their subtasks. So in that way, everything collects up to the root. And that's also how the agent or this UI can know about everything. But you don't get to know the graph of tasks in advance. And that is a little bit of an issue for the typical like data processing use case, because the tasks can create whatever subtasks they want. Yeah, you have no idea basically. You might create 10 subtasks or 100, and they might do whatever.
That's a good continuation. Is there anything stopping you from accidentally creating unlimited amounts of tasks? All right.
No, and it relies on Kubernetes to do the scheduling. It will try to deploy as much stuff as it can, and you can give it like memory requirements, and then they will wait if there's nothing available. And the idea there was that you would have auto-scaling on the cluster, and you would just want to run as much stuff as possible, and you can let the cluster scale and then scale down later.
All right. Thank you.
I just got an idea. So if you have a parent which launches multiple children job and it gets result from one children, which means that it shouldn't continue, can you kill the other ones?
Yeah, like if the parent decides to quit before the children are done, they will be killed off.
They will be killed off.
Yeah.
Cool.
There is a kill family function somewhere. Yeah. Yeah.
What better way to end this? I think that Peter is pulling our attention. Right?
Yeah.
Thanks a lot, Johan.
Yeah. Thank you.